And we is live. We is very live, very live. All right, let me close some windows. A few windows, very few windows. La 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 la. La 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 la. So the microphone, we need to unplug and re-unplug. Okay, so the microphone is USB, but the speaker is not USB. All right, let's look at the volume control. Looks very good. Switch device. Let me share this so I can fix this and that and this and that. Yeah, the input is USB, but the output is the nut. Okay, so maybe we shouldn't switch each time. I think we're done with Professor Lenny. Oh, her name is How. Okay, How. Yeah, that's what I thought. Okay, so this is not useful. Now we do need to listen to the audio and open it on the X phone. Num 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 and num 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 num. Yeah, it's very good. The best. We have the best audio. We have the best audio. La 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 la. Let me give you the link. The link is in the bio. The link is in the bio. Yeah, I don't think we need anything else. It's going to be just another boring conversation. So we made a mistake last night. A big mistake. A very big mistake. Mistaken identity. I wrote it in the comment section. Wait, we can close this girl. So in the comment section there from yesterday. So after I finished the stream, I was listening to it because it was so enjoyable to listen to. I actually enjoy listening to these streams because it's actually it's good stuff. La 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 la. So I said I forgot to multiply by 24 hours. So we need to divide by 24 before we take the square. So it's even we'll need much more than what we thought last night. Much more. It's probably going to be a few tens of thousands of dollars of fiber optic. So we might need to maybe buy a bigger stockpile of the fiber. Also, if you don't unpack it, you're going to get an interference. No, if you don't unpack it, there's not going to be a difference because we'll have to think about the vertical. We'll think about that. Okay, much to talk about. So where were we? We need to talk about, first of all, the 24. Let's multiply by 24. La 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 la. We need to la 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 la. It's not 8,500. So before we got to the 8,500, the fiber optic. Can you see my big mouse? Oh, now it's tiny. La 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 la. Let me see if you can see the big. I changed it to a big cursor. No, I don't think you see the different size. I have a bigger cursor now, but you don't see it as bigger. So it's useless. So it's just an inconvenience for me. Okay, I'll change it back later. Where's the 8500? I guess 6 times 2. Anyway, this is not 3600. This is 36 times 24. So what is 36 times 24? It's basically 35 times 25. What is that? Who knows? I don't know. But it's approximately, well, it's like 40 by 20. It's 800. It's about 800, or about 1,000. It's basically 40 times 20. So 4 times 2 with 2 zeros. So it's about 800. So it's not 36. It's 800. So it's not times 10. It's times 20. So let's get this right this time. Okay, so let me pull up the calculadora. Calculadora, la 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 dora, la 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 la. La 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 la. Let's close this window. La 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 la. La 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 la. 6378 times 2 pi. We need to write these things down somewhere. I wish I could have more papers. Anyway, 6378 times 2 pi times 2 times pi, which is 6 times 6 is 36. It's 40,000. Okay, so 40,000 divided by 3600 divided by 3600 is 11. Okay, so this is 11,000 because it's kilo. So it's 11,000. There's meters per second. So it's 11,000 meters per second. Almost. Then you need to divide by 24. So, because we forgot to bring over the 24. So divided by 24, and this is 0.464 meters per second. That doesn't make any sense. Times 1,000. Times. So it's 500. So that's what I thought. It's 500 at the equator. It's around 500 at the equator. Or 464. It's 464 at the equator. This is 464 meters per second. What is this dv theta, d theta? Oh, so dv phi. So we did here the phi exercise. It's 464. This is incorrect. This is incorrect. I mean, it's mostly correct. So let me just put the corrections. This is times 24. This is times 24. So this is divided by 24. It's 11,000 divided by 24. It's 464. So let's go to the next. So assuming it's 464 at the equator, now it's going to be completely different. So it's not 8500 at all. It's 464 at the equator, not 8500. La 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 la. Let's undo. So it's not 85, it's 464. 464. All right, so 464 divided by 3 times 10 to the 8th. So 8 power 10, that's 100 million, times 3. So that's 300 million divided by 464 divided by 464 is equal to, now invert it and now square it. So it's 2.39 times 10 to the negative 12. So this is incorrect. This is 2.39, 2.39 times 10 to the negative 12. Okay, so that's what this thing is. And this thing is 0.3. And this is nanometers. So we need to take this, divide by 0.3. Is it exactly 0.3? 65 divided by 2 is 0.325. Yeah, because the nanometers, it's approximately 0.65 micrometers. This can vary, so it depends on the light we're using. It could significantly vary. Nevertheless, so let's just, so we have this number. Let's do this again. So this is 0.325. Let's do what? 200 divided by 650. 200 divided by 650. No, it's 0.31. Why did I get it? 65 divided 6 over 2 and 5 over 2. The 5 over 2 is 2.5. So shouldn't be 325. What am I missing? Yeah, this is 325, but it's 1 over 325. If I do 1 over, yes, 3.25 inverted is 0.308. So this is 0.308. That's insignificant. Okay. So 0.308, anyway, this is nanometers. So, and this is meters too. So the meters go away. So we're left with the nano. Nano is -9. So remove this and put here a 10 to the 9. So the 9 here goes away and we remove 9 from the 12. So it's 3. So this is 3. La 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 la. So it's 0.308 over 2.39. So we'll take this. So it's 2.39 times 10 to the negative 3. So let's just put here 10 to the 3. So it's 0.308 divided by 2.39 times 10 to the third. So 0.308 divided by 2.39 is equal to 0.129. 0.129 times 10 to the third times 1,000. 128.9. 129. That's impossible. Can't be 129. Should be maybe 0.129. 1, 2, 3. Yeah, I multiplied by 1,000. One too many times. Yeah, we need to take small steps. Yeah, let's write down the intermediate steps, otherwise we're going to lose our minds. All right, so 464, so we have this. Is this right? 2.39 times 10 to the negative 12. This is what this comes out to be. Well, it's 8 squared is 16. 16 minus 1, 2, 3. 16 minus 3 is 13. We got a 12. It's basically the same. So this is the right number, approximately. That's this thing. And this is the right thing, except for the nano. The nano is 9. So 10 to the 9 and 12. So we remove the 9. The 12 minus 9 is 3. So it comes up 10 to the third. And all we have left is 0.308 divided by 2. So it's 1/3 divided by 2 1/3. So it should be 2, it's 3 and 3. That's 6, 7. Basically 7, maybe 8. 8 point something. It's 1/8. So it's 0.125 times 1,000. It's 125. How could it be? It should be a smaller number than we got yesterday. Instead of 8,500, we have 464. It should come out as a smaller number than 0.3. Right, it used to be 10 to the minus 10. Now it's 10 to the minus 12. It's much smaller. So what did I miss? Unless nano is wrong. Micro is 6. After micro is nano. It's just 9. If it's 9 at the bottom, it's not negative 9 at the bottom. What am I missing? 85. It's 464. What am I missing? Let's start over. It's 2d divided by lambda times v over c squared. 2d is about 200. Lambda is about half a micron. Let's say it's about a micron. Half a micron. Micron is the same. So let's say a micron. So 200 times a million is 200 million. So it's 200 million. Okay. So this is 200 million. And this is 500, let's say 300. 300 divided by, wait a minute, this is not 464. Because we need to do the phi it's in Ohio. It's 80% of 464, so it's about 300. It's ballpark. So it's about 300. The 300, 3 over 3. So it's 100, 10 to the 8. 10 to the 8 minus 100, it's 8 minus 2 is 4. 10 to the 4th, but it's squared, so it's 10 to the 8th. So this is 10 to the negative 8. This is just 10 to the negative 8. And this is 100 million. So it's 10 to the 8th. So it's 1. So it should come out as 1. Because this is, we said 100 million. Because we're ballparking. This is 100. And we said it's about a micrometer. So it's a million. So it's 100 million or 200, whatever. It's 100. This is 100 million. So this is 10 to the 8th, and this is 10 to the negative 8. So it's 1. So it's 1 tick. That's impossible. Before it was 0.3, when it was 8,500. How could it be 1 when the number is significantly smaller and is squared? So it's even smaller. It has to be much, much smaller than 0.3. But it looks correct. Again, so this is 300 over, right? This is 3 times, so remove the 3. So it's 10 to the 2 and 10 to the 8. Oh, wait a minute, this is 6. Sorry. 8 minus 2 is 6. 6 squared is 12. So this is negative 12, and this is 8. So it's 12 minus 8. 12 minus 8 is 4. This is 1 in 10,000. Yeah, that makes more sense. Jesus Christ. This is why, this is what happens when you work without Excel. Really, we should be using a spreadsheet so that we avoid all these endless mistakes. Maybe I should work with a spreadsheet. This is just too dangerous. I shouldn't be doing these calculations. Oh my God. How's the audio? Oh my God. How's the audio? Yeah, sorry. I have an itch. Okay, let's drink some water. La 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 la. Okay. So this is 200, which makes sense why they had no chance. They had no chance. No chance in hell. No chance in hell to get this. No chance in hell. No chance in hell. No chance in a million years. Michelson and Morley had no chance. Absolutely hopeless. Horizontal. Vertical, we can talk about that, but horizontal, this is a squared ratio of 300, of basically 1 to a million. So this is negative 12. What is negative 12? This is what's after nano? It's pico. This is a picopart. This is 100 million. So this is negative 12, and this is 8. 12 minus 8 is 4. This is 10 to the negative 4. This is 1 over 10,000 of a meter. Sorry, it's unitless. It's times. That's the part of the wavelength over 90 degrees, right? We're assuming here a 90-degree rotation. Where did we assume the 90-degree rotation? No, we're asking how many ticks can you get? This is the number. I did the calculations. This should give me the number of ticks. Over 1 degree or over 90? I think over 90 degrees. I think this is assuming 90 degrees. It's already loaded. The 90 degrees is already assumed. This is the number of ticks. Somehow it's already assumed. Because we had delta L, delta T. We started with delta T, and we had delta L. Where did we assume that? Oh my God, it's impossible to look back. This one, I think. This is the evolution of the equations. So this is where we started. So we had delta T. I wish this wasn't stuck here. This thing is stuck in the middle of my life. Maybe if I tap this, it's always there. Oh my God! Ah, forget it. Okay. So we started with delta T. So the delta T between the two of them is this. Delta T times C is delta L. But where's the 90 degrees? There's no 90 degrees in here. This is just the expected difference. Where is the angle of rotation in this consideration? So the number of wavelengths is the delta L. Delta L, this is, there's no, N is not the number of ticks. This is just the number of wavelengths. Okay, so delta L is delta T times C. So delta L is equal to delta T, and delta T is this, dV squared over C cubed, dV squared over C cubed times C, so it's just dV squared over C squared. That's delta L. Okay, but that's it, regardless of the rotation. Where's the rotation? We did the calculation per degree or per something. So where is that? We should number these, the pages, otherwise we're going to get lost. So I think this is number 2. So the number of ticks is 2 times over 90 degrees is 2 times the number of lambdas. Why is it 2 times the number of lambdas? Which is 2 delta L over lambda. Why? The number of ticks over 90 degrees. Why is it 2dv squared over c squared lambda? I don't get it. Where do we get this? This is over 90 degrees. Why is it over 90 degrees? Why would you assume? I'm assuming here that the number of ticks over 90 degrees is just twice the number of lambdas. The number of lambdas. Why would you assume that? What? Why would you ever assume that the number of ticks over 90 degrees, that means how many lambdas are we going to encounter while we rotate the entire apparatus by 90 degrees? Where's this coming from? As I'm rotating by 90 degrees, what is happening? I mean, you could get many ticks. Why are you assuming just double? What? Why are you assuming just 2n? I don't get it. And lambda is just delta L over lambda. I don't get it. Which is delta L is delta Tc. And delta T is 2dv squared over c cubed. That's all fine, but where did this come from? We must have done, there must be a page of calculations with, that we ended up with this. This is a weird result that it's just 2. Why is it just 2 times? Why is the number of ticks, the number of times we're going to cross, we're going to have a complete wavelength interference as we rotate the apparatus by 90 degrees is just going to be 2 times the number of ticks for lambda. It's not even the number of ticks for lambda, it's just the number of lambdas. The number of lambdas is how many lambdas are we going to have? Like, what is the difference? So I guess I'm saying after 45 degrees, it's 1. Well, this is the number of lambdas. Yeah, this is beginning to make sense. The number of lambdas is delta L over lambda. That makes sense. But we know that during 90 degrees, we're switching sides. The fast becomes the slow becomes the fast. After 45 degrees, we've covered all of our lambdas. It's symmetric about 45 degrees. It makes sense. There is a rationale. But we should have notes about this. There should be a page of notes. I wish I could just go through all the notes page by page. I wish I could look at them quickly. Maybe there's a way to save it in general. Maybe there is a way to export all of these drawings. Can I just export these drawings somewhere so I can look at them quickly? La 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 la. What is this? Is this garbage? This is garbage. We can throw this away. Garbage. All right. So this is black hole. This is the speed of light. This is GR. This is wave mechanics. What is this? This is the double slit experiment. La 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 la. What just happened? La 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 la. Let me text him that I cannot talk. La 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 la. Wow, why can't I? Oh, it doesn't let me see phone calls. All right. Okay. All right. Oh, we have messages. 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 Oh my God. Joe's incarnate. Who is? I remember the name. The interferometers in LIGO, they don't rotate, so they're useless. Are designed to detect incredibly tiny. Yeah, but they don't rotate. Changes in the distance between mirrors caused by passing gravitational waves. The precision required for this is astonishing. Oh my God! Everybody's calling me. What is going on here? La 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 What is this? That's garbage. Okay, so we have to finish. Okay, Jules, I'll be back. I can see your comments. Good comments. I'll respond in the next session. Let me. Yeah, of course. Of course, I check everything. I'm actually interested in getting actual results. All right, I'll be back in a couple of minutes. Bye.